We know about transcendental functions now, and transcendental functions are functions like e to the x and the natural log of x. And now we're going to learn about L'Hopital's rule. And L'Hopital's rule is used when you're trying to determine the limit and you get an indeterminate form. So, why are we doing this? Well, pretty soon we're going to be taking integrals, and the limits of integration are going to involve infinity, and I might get indeterminate forms when I take that limit, when I evaluate it, so it's important that we know how to deal with that now. So L'Hopital's is a rule, and I'm going to show you tons of examples on how to use it. But first of all, let's go ahead and write out some criteria for it. L'Hopital's rule is used when you get an indeterminate form when taking limits. Now, there's a lot of different indeterminate forms. But there's a couple that are called indeterminate L'Hopital's. So the ones that we're interested in are indeterminate L'Hopital's are 0 over 0. And I abbreviate L'Hopital's L'H, or any plus or minus infinity over any other plus or minus infinity. These are called indeterminate L'Hopital's. Now, I have any of these forms, when I take a limit, I can apply L'Hopital's rule. And again, I haven't told you what L'Hopital's rule is yet, but I'm going to write out the criteria first and then show you the rule. Now, L'Hopital's rule can only be used when it is applied to one of these forms. So if I get any other limit, I can't use L'Hopital's rule. Okay, only these two forms. So that's something that we need to remember. So again, it can only be applied to limits that give you that indeterminate form of 0 over 0 or infinity over infinity. It applies to one-sided limits as well. As well as the two-sided, meaning both sides. We check from both ways. Okay, and then what we need to think about is, what if you get something besides 0 over 0 or infinity over infinity and you still can't evaluate the limit? Well, if you get a non-L'Hopital's indeterminate form, there's other things that we can do to get it into a L'Hopital indeterminate form to work with. So the non-L'Hopital indeterminate forms might be something like 0 times infinity, infinity minus infinity. Those are a couple of examples. And if we get these, they're indeterminate, meaning I can't figure out the limit, but not L'Hopital's. So what I would do if I get one of these forms is I would rewrite, factor, cancel, get rid of layered fractions or put layered fractions in. Those are some strategies that we could use here. Now there's another type of indeterminate form, and these are indeterminate powers. So these would be things like 1 to the infinity, 0 to the infinity, or infinity to 0. These are also indeterminate, but not L'Hopital's. Now what do I do with these? Well, these often come from a setup where we have a variable to a variable. So it came from a function that looks like a variable in the base and a variable in the exponent. So for instance, like x to the sine x, or something like sine x to the natural log of x, something like that. So if this is the case, a lot of times what can happen, or what will help us out, is to handle it with the natural log. So use the natural log to rewrite. Okay, so those are kind of our strategies, and what I'm going to do is we're going to work a lot of problems so we can talk about strategies for each one as I explain what L'Hopital's is. Now, one more thing about L'Hopital's, you can apply L'Hopital's as many times as you need to until you get an answer. But as you're applying it, at any point along the way, if you don't get an indeterminate L'Hopital form, you have to stop using it and find another method. So you can only apply L'Hopital's multiple times if each iteration or each time you apply it results in another indeterminate L'Hopital's form. Okay, so you can use this over and over again, but it has to be indeterminate L'Hopital's at every step. If there's ever a time that it stops being indeterminate L'Hopital's, you're going to have to stop applying it and find another method. Okay, let's start looking at some problems, and I will explain what L'Hopital's is as we go. Let's look at the limit as x approaches 0 of x cubed over x. Now I know we can simplify this, we can reduce this to x squared, but I want to explain to you how L'Hopital's works based on this being not simplified. So if we go ahead and take the limit as is without rewriting first and plug 0 in, 0 cubed is 0, x is equal to 0. So 0 over 0 is indeterminate L'Hopital's. That's one of my indeterminate L'Hopital's forms. So what I'm going to do here is to go ahead and apply L'Hopital's. Well, this is what L'Hopital's is. L'Hopital's says to take the derivative of the numerator and the derivative of the denominator and then try the limit again. Now this is not the quotient rule. I'm not taking the bottom times the derivative of the top or anything like that. I'm just doing a straightforward derivative of the top and the derivative of the bottom. So in rewriting this, I have the limit as x approaches 0. The derivative of x cubed is 3x squared. The derivative of x is 1. And now when I take the limit and I plug 0 in, I get 3 times 0 squared is 0. 0 over 1 is 0, and that's my limit. Now I would have gotten that limit if I would have reduced this and simplified and then taken the limit as well. But I just wanted to show you how L'Hopital's works in a very basic form. Let's look at another one. Let's look at the limit as x approaches 0 of x over x squared. Now again, we're going to look at this, and I could reduce this, the x over x squared first, but I want to go ahead and apply L'Hopital's. If I take my limit, I get 0 over 0, and this is the work that I need to show. I say indeterminate L'Hopital's, so I have to explain each step. So indeterminate L'Hopital's says I can then take the limit as x approaches 0 of the derivative of the numerator over the derivative of the denominator. So the derivative of x is 1, the derivative of x squared is 2x. Now when I plug 0 in, I get 1 over 0. Now that is not indeterminate L'Hopital's. Okay, this is undefined. And remember, the triangle with 3 dots means therefore the limit does not exist. So we probably have not talked a lot about limits since Calc 1, but we use an abbreviation there, DNE, does not exist. I want to talk more about this because not only does the limit not exist, but I could probably figure out if it's approaching positive or negative infinity if we plugged in some values here, or if I recognize this parent graph. So this graph of 1 over 2x looks something like this. So this is y equal 1 over 2x. Now as we approach 0 from the right, this is going off toward infinity. As we approach 0 from the left, it's going toward negative infinity. So these two sides don't agree, and so therefore the overall limit does not exist. So sometimes I can look at this and say, okay, it's approaching infinity, it's agreeing, but this one is not. Okay, so the limits do not agree from either side. Okay, let's go ahead and look at a few more. Let's get some trig in here. So 3x minus sine of x and all over x. So let's go ahead and plug directly in. So this would be 3 times 0 minus sine of 0 all over 0. That's 0 minus sine of 0 is 0 over 0. 0 over 0 is indeterminate L'Hopital's. So I have to do more work. So do more work. Keep going. Okay, so indeterminate L'Hopital's, then I would come back here and I would say, okay, then I can take the limit as x approaches 0 of the derivative of the top all over the derivative of the bottom. So the derivative of 3x is 3. The derivative of minus sine x is minus cosine of x. The derivative of x in the bottom is 1. So let's go ahead and take that limit again. This would be 3 minus cosine 0 if we plug directly in. Cosine of 0 is 1. 3 minus 1 is 2. And that is my limit. So get in this habit. Indeterminate L'Hopitals, do more work. Okay, so don't stop if you get indeterminate L'Hopitals. You're not done yet. Okay, let's keep looking at lots of examples so we can start seeing some of the patterns and trends and maybe some of the rewrites. Well, and we'll run into some that don't fit our cases, and we'll have to learn some new techniques. Let's look at the limit as x approaches 0 of the square root of 1 plus x minus 1. Notice the minus 1 is not under the integral, or sorry, the square root sign. It's not part of the radical. So let's go ahead and plug 0 in. 1 plus 0 minus 1 all over 0. So 1 minus 1 over 0, 0 over 0. That is indeterminate L'Hopitals, and that means do more work. DMW, do more work. Okay, so the more work we need to do is to apply L'Hopitals since it's L'Hopitals form. I'm going to take the derivative of the top, so that's going to be 1/2 1 plus x to the negative 1/2 times 1. The derivative of the bottom, the derivative of x is 1. So if you're wondering where that came from, if you don't recognize it, this is the same as 1 plus x to the 1/2, and so we just use the chain rule on it. So let's go ahead and simplify this. I want to get rid of that negative exponent. So I'm not taking the limit, I'm just rewriting what we have here. So 1 over 2 square root of 1 plus x. And that came from this moving to the denominator and then this flipping down into the denominator. So let's go ahead and take our 0 here. And I'm going to be left with 1 over 2 times the square root of 1, which is 1/2. So that's the limit. And remember, you have your calculators. You can certainly graph these. Some of them graph really nice, some of them not so much, depending on the function. You might have to adjust your screen quite a bit, or your window, I should say, on your calculator. Now these are a lot of work. They take up a lot of space, but I would say that it's really just a lot of algebra. So the calculus is only applied at each step where we take a derivative. The rest of it is rewriting and getting these into some indeterminate forms. So the first thing we do is we just plug in whatever value is our limiting factor as x approaches 0. We just plug it in and see what we get. If we get a nice answer like 12 or -2, we're done. So if we plug that in, we get square root of 1 plus 0 minus 1 minus 0 over 2 all over 0 squared. So square root of 1 is 1, so I get 1 minus 1 minus 0 over 0. 0 over 0 is indeterminate L'Hopitals, and that means to do more work. Okay, so the more work we're going to do is to apply L'Hopitals rule, since this was an indeterminate L'Hopital form. So the derivative of 1 plus x, I can rewrite that as 1 plus x to the 1/2. So when I take the derivative, I'd bring the 1/2 down, decrease the exponent by 1, and then multiply it by the derivative within. The derivative of 1 is a constant, the derivative of 1 is 0, and the derivative of minus x over 2 is minus 1/2. And the derivative of x squared is 2x. So right now I can see that if I took the limit, this would go to 0. I'm not sure right here. I guess we could flip it, or we could go ahead and take the limit. I think we're going to get 0 over 0 again. So let's go ahead and check that out. So I'd have 1/2 times 1 plus 0 to the negative 1/2 times 1 minus 0 minus 1/2 all over 2 times 0. So let's analyze this. This is 1 to the negative 1/2. 1 to any power is 1. Half of 1 is half. Half minus a half is 0. So I get 0 over 0 here, which is indeterminate L'Hopitals, which means to do more work. Okay, so we have the second iteration of L'Hopitals here. These are cool. Okay, So now I'm going to have to take the derivative again. So I already have this 1/2. I bring the negative 1/2 down, decrease the exponent by 1, and then multiply it by the derivative within. The derivative of 0 is 0, the derivative of 1/2 is 0, and then the denominator, the derivative of 2x is 2. So let's go ahead and take that limit. So I have a negative 1/4, and then I have a 1 to the negative 3/2 all over 2. Well, this piece right here is just 1 to any power is going to give you a 1. And I have a negative 1/4 over 2. And I could write that as 2 over 1. And remember, when you divide by a fraction, you multiply by the reciprocal. So for this particular case, I don't think that's right. I think I flipped it wrong. Sorry. So when I flip it, 2 over 1 becomes 1 over 2. And then I get negative 1/8 for this particular case. Okay, so again, as usual, like I say on everything, show lots of work. It's going to help you kind of find the right path through this. And then if you make a silly mistake like I just did at the end, and you have all this great work, you won't lose all your credit because you have lots of work to show the supporting of what you did. So the more work you show, the better. And that what I want to see at the very least here is at every iteration tell me that it's indeterminate L'Hopital's, because not everything is. And then if it's not indeterminate L'Hopital's, I have to use some other methods to get to that limit. Okay, let's look at the limit as x approaches 0 of x minus sine of x all over x squared. Okay, so we plug 0 directly in, so I have 0 minus sine of 0 all over 0 squared. Sine of 0 is 0. This is 0 over 0, which is indeterminate L'Hopital's, which means to do more work, DMW. So the more work that I'm going to do here is to take a derivative. The derivative of x is 1, the derivative of sine of x is cosine of x, and the derivative of x squared is 2x. So let's go ahead and take that limit again. Cosine of 0 is 1, so I get 0 over 0. This is still indeterminate L'Hopital's, but that's good because if it's still indeterminate L'Hopital's, I can keep using it. So here I'll have the limit as x approaches 0. I'm going to take my derivative again. The derivative of 1 is 0. The derivative of negative cosine is, the negative is already here, so that's from here, is negative sine. And the derivative of 2x is 2. So this is just the limit as x approaches 0 of the sine of x over 2, which is the sine of 0 over 2. Sine of 0 is 0. So we get 0 here. Wait a minute. Okay, on this next one I was looking at, this is really a good one. We're going to be using a transcendental function, and transcendental means exponential, logarithmic. And that's really, L'Hopital's is really good for those. It works for all sorts of other things too, but it's nice that it works for those. Let's take the limit as x approaches infinity of the natural log of 1 plus 1 over x all over, and we get some trig too, sine of 1 over x. Now, let's make sure we note this. This is a limit as x approaches infinity. So a lot of these that we've been doing up above have been 0 or another number, but this is infinity, so this we really need to start thinking about what infinity is saying. Okay, so when I first plug in to take my limit, I have the natural log of 1 plus 1 over infinity. Now technically we can't plug in for infinity, but we can kind of visualize what it's doing though. If I have the number 1 and then I'm dividing it by numbers that are larger and larger and larger, so 1 divided by 100, 1 divided by 1,000, 1 divided by 1,000,000, 1 divided by 1,000,000,000, this is getting smaller and smaller and going towards 0, and so is this one. So on the top what I end up with here is the natural log of 1, and in the bottom I end up with the sine of 0. Well, both of these are 0, so 0 over 0 is an indeterminate L'Hopital's form, and that means to do more work. Okay, so the derivatives here are going to get pretty interesting. So the limit as x approaches 0. The derivative of the natural log of u is 1 over u times the derivative of 1 plus 1 over x. Well, the derivative of 1 is 0, and the derivative of 1 over x is negative 1 over x squared. Okay, the derivative of the sine of u is the cosine of my argument times the derivative of my argument. So just as a quick note here, the derivative with respect to x of 1 over x is the derivative with respect to x of x to the negative 1. So that's negative x to the negative 2, which is negative 1 over x squared. So that's where that's coming from. Okay, when I simplify, these cancel, and I'm still working on my limit. And I have 1 over 1 plus 1 over x cosine 1 over x. Now, as x is going toward infinity, 1 over x goes to 0. So does 0 for my argument here. So here I'm left with 1 over 1 plus 0 is 1, and the cosine is 0, which is 1. So this limit is equal to 1. So why does the limit as x approaches infinity of 1 over x equal 0? Well, let's think about what the 1 over x graph looks like. So as x goes toward infinity, this is going toward 0. And if x is going toward negative infinity, this would also be going toward 0. A couple things to think about. And if the numerator is fixed, like the number 1 is fixed, and the denominator is increasing without bound, that fraction is getting closer and closer to 0. So there's a couple things to think about there. Let's look at the limit. On this one, we're doing x approaches 0, 1 minus cosine of x all over x plus x squared. Okay, let's go ahead and plug directly in. See what we get. Cosine of 0 is 1. 1 minus 1 is 0 over 0. This is indeterminate L'Hopital's, which means do more work. So the more work we're going to try is to apply L'Hopital's. The derivative of 1 is 0. The derivative of minus cosine x is minus a negative sine of x. The derivative of x is 1. Derivative of x squared is plus 2x. So let's rewrite this. Minus a negative is the same as a positive. Okay, and let's plug that 0 in. So I get sine of 0, 1 plus 2 times 0. Sine of 0 is 0. 0 over 1 is 0. So this just had one iteration of L'Hopital's to apply. But you're probably getting an idea of some of the patterns that you're going to see here. It's always really important that you take and look at the limit to see what the limiting value is, whether it's 0, infinity, or a different constant. Now, L'Hopital's can be applied to one-sided limits as well. So let's look at the L'Hopital's for sine x over x squared. Now notice here, x is approaching 0, but only from the right. So when I approach 0 from the right, I'm only talking about positive numbers that are very, very small. So visualize 0 from the right, and we'll also draw a graph out here in a moment. So the way we treat this is we plug it in right away, just as we usually would. So I get 0 over 0 is an indeterminate L'Hopital's, and that means to do more work. Okay, so let's go ahead and take the limit as x approaches 0 from the right. The derivative of sine x is cosine of x. The derivative of x squared is 2x. Okay, so go ahead and plug in cosine of 0, and we can put from the right if you want to. And then 2 times 0 from the right. The cosine of 0 is 1. 2 times 0 is 0. This is not indeterminate. This is undefined. I have to stop. I can't use L'Hopital's anymore. Plus, what that's saying to me at this point, if that's undefined, is the limit does not exist. DNE does not exist. So when we talk about that, when we're trying to figure out what exactly is going on with this limit, 1 over 0 means probably that there's an infinity involved. So a lot of times what we like to do is we like to figure out, okay, is this approaching plus or minus infinity? You know, what's going on with that? So what we could look at is the cosine of x over 2x. Think about the cosine graph. Cosine graph looks something like this. This is pi over 2, pi, 3 pi over 2, and then 2 pi. Well, as we approach from the right and we get closer and closer to 0, you can see that all of my cosine values are positive. Now in the denominator, as I approach from the right, all of these values will be positive as well. So this ends up being some positive over positive until we get to that actual point. So what we can say here then is that this limit as x approaches infinity is definitely undefined. It does not exist, but what we need to figure out is which infinity it approaches, and this approaches positive infinity, and so our limit does not exist. So we already established that we had a positive on the top, positive on the bottom, so positive over positive is positive infinity, but that's also telling me that the limit still doesn't exist. So that's not my answer, that's just explaining why it's undefined and that it doesn't exist. Let's look at another limit involving a trig function. Let's approach pi over 2, and this is from the left. Let's look at secant x over 1 plus tangent x. Okay, so this will be good. So I go ahead and plug in the pi over 2. So I have secant pi over 2. And remember, I'm only approaching from the left. If that becomes an issue, something's undefined, which it's about to be. Okay, so secant is 1 over cosine. And cosine at pi over 2 is 0. So I have undefined on the top. In the bottom, I also sine over cosine for tangent would be 1 over 0. So I have undefined over undefined. Okay, so 1 over 0, 1 over 0. So what I need to do here then is to think about, okay, what could I do to rewrite this? This is definitely not a solution, but it's kind of pushing me in the direction of finding a different method. Well, like we talked about above, when we get 1 over 0, that's undefined, but that usually means we're approaching either positive or negative infinity. And in this case, for cosine, I know I'm approaching positive. Now, 1 plus 1 over 0 is still undefined, but that also means that I'm approaching some sort of infinity when it's undefined. Now this is indeterminate L'Hopital's, and I need to do more work. So let's look at the limit as x approaches pi over 2 from the left. Now the more work I need to do is up here. The derivative of secant x is secant x tangent x. The derivative of 1 is 0. The derivative of tangent is secant squared. So I clearly see that I can do some simplifications here. This cancels and leaving me with the secant in the denominator. So I'm left with tangent. Actually, I'm going to rewrite that. Tangent is sine over cosine. Now secant down in this denominator is 1 over cosine. So remember, when you divide by a fraction, you're multiplying by the reciprocal of the denominator, the overall denominator. So this is sine over cosine times cosine over 1. These cancel, and then I'm left with the limit as x approaches pi over 2 from the left of the sine of x. So I can plug that directly in. The sine of pi over 2 is going to be equal to 1. Okay, so this one is a little bit sketchy right here. I had to remember that 1 over 0 is undefined, but that usually means that I'm approaching infinity of some sort. So as we're working through these, it seems like we get zeros and ones a lot. It's not always the case. We'll have some different ones coming up. Always check for does not exist as well. because not every one of these will have a limit that exists. Let's look at the limit as x approaches infinity of natural log of x over 2 root x. Now it's my theory, and I could be very wrong, but it's my theory that the more you practice math, the better you get at it. So that's why I'm going through and doing a lot of these problems with you, so you get to be exposed to all sorts of different functions, all sorts of different tricks. And again, the more you work, the better you'll get at these. So if the first time it doesn't work out, keep trying. So the natural log as x goes toward infinity, well, the natural log graph looks like this. So as x goes toward infinity, you can see that it's increasing very, very slowly, but it's still increasing. So this is equal to infinity over infinity, because 2 times the square root of infinity is infinity. So this is indeterminate L'Hopital's, which means to do more work. Okay, the natural log of x. The derivative of the natural log of x is 1 over x. The derivative of x to the 1/2 is 1/2 x to the negative 1/2. So that's the derivative of this piece right here, is right down here. And if you're not sure how to get that, you would rewrite square root of x as x to the 1/2 and then take the derivative. Well, this is not ready to evaluate. I think I can do quite a bit of simplifications here. First of all, I notice that the 2 and the 1/2 cancel. And then I also notice I could rewrite this this is pretty layered up, so let's get rid of some of the layers. So this is x to the negative 1 over x to the negative 1/2. And then rewriting there, I'd flip the x to the 1/2 up top, the x to the first down into the denominator, and this is going to leave me with 1 over x to the 1/2. Well, as x goes toward infinity, the numerator is fixed, the denominator is increasing without bound. That goes to 0. So we got another 0. Let's hope we don't get zeros and ones for all of these. Okay, let's go ahead and introduce an e to the x here. So when I take my limit right away, e to the infinity equals infinity, infinity squared equals infinity. This is an indeterminate L'Hopital's, which means to do more work. The derivative of e to the x we have lately learned is e to the x. The derivative of x squared is 2x. Take our limit again and I get infinity over infinity, which is an indeterminate L'Hopital's, which means to do more work. Limit as x approaches infinity. The derivative of e to the x is still e to the x. The derivative of 2x is 2. So now I get infinity over 2, which is infinity, which implies that the limit does not exist. That's not an indeterminate L'Hopital form, so I don't keep going, I stop. And saying infinity is the answer is not the end of it. You have to say that means the limit doesn't exist. It's explaining why it doesn't exist, but we have to explain what infinity means when you get that for a limit. Let's look at the limit as x approaches infinity of x sine 1 over x. So if I look at this right now and plug directly in, I'd get infinity times the sine of 1 over infinity. Well, we know that this piece goes to 0, and the sine of 0 is 0. So this looks like infinity times 0. Well, that's in indeterminate form, but it's not L'Hopital's. So what I need to do is think about rewriting and then do more work. So one of the tricks for these, for the rewrite, is to, it's kind of funny, to take this and then get it into the denominator somehow. So let's think about that. So I'm going to have the sine of 1 over x. Where did this x come from? Where could I have flipped it from? Well, if I had 1 over x in the denominator, I could flip this and it would become x over 1, and then you can see I'd have this right back. Now this is a trick we do a lot in this section, so just always remember that. You can always flip this, and you just don't flip it directly down like this. You have to think, where did it come from? It came from dividing by 1 over x, and then the x pops up top. Okay, as x approaches infinity, I have the sign of 1 over infinity, all over 1 over infinity. And I actually don't like writing it like that, but that's kind of our thought process anyway. So this looks like the sine of 0. And then 1 over infinity, 1 is fixed. The denominator is increasing without bound, and so that's going towards 0. And now I have my 0 over 0, which is my indeterminate L'Hopital form, which means to do more work. Okay, so the more work that I'm going to do is take my derivative. The derivative of the sine is the cosine of 1 over x times the derivative of 1 over x. And the derivative of 1 over x in the denominator is negative 1 over x squared. So these cancel, and I'm left with the limit as x approaches infinity of the cosine of 1 over x. Now as x goes toward infinity, remember this is a fixed numerator. Denominator is increasing without bound, so this is going toward cosine of 0, and we know the cosine of 0 is 1. So we got another 1. So a lot of these are, like I said, zeros and ones. But the key on this one was we did not get an indeterminate L'Hopital's form right away. I got an indeterminate form, but I had to rewrite it and get it into an indeterminate L'Hopital form before I could deal with it. Okay, let's look at another one. This one is going to be interesting. It's a one-sided limit and a natural log. Okay, so the first thing we do is plug directly in. So this would be square root of 0 from the right, natural log of 0 from the right. So this is 0 times, this is negative infinity. So let's remember what the natural log graph looks like. This is the natural log graph. So as we approach 0 from the right, we can see that this is dropping and going toward negative infinity. So this is indeterminate, but not L'Hopital's. So my key here is to rewrite. Okay, so limit as x approaches 0 from the right of natural log of x all over, and I'm going to flip just like I did the last one. So let's think about this. If I took the natural log of x all over 1 over root x, when you divide by a fraction, you multiply by the reciprocal, so that root x comes up top. So that's why I can rewrite this to get that root x where it started from. It's just another way to rewrite. So this is just a quick little note here. Whoops. I don't know if I can change the, guess I can't change the color of it. So note. Okay, so let's go ahead and take that limit now. The limit as x approaches 0 from the right of the natural log we know is negative infinity. Okay, and then let's look at the limit as x approaches 0 from the right of 1 over the square root of x. Now let's think about what that graph would look like. If I plug 0 directly in, it's undefined, but I'm only approaching 0, and I'm approaching 0 from the right. So let's look at the graph of 1 over the square root of x. Looks something like this. So as we approach 0 from the right, I can see that this is going off toward positive infinity. So this is also an indeterminate form of negative infinity over infinity. So knowing your basic parent graphs is really helpful here. So this is indeterminate L'Hopital's, which means to do more work. Okay, so the more work as the x approaches 0 from the right. The derivative of the natural log of x is 1 over x. And then the derivative of 1 over square root of x is the derivative of x to the negative 1/2. So this is negative 1/2 x to the negative 3/2. And we could just put that right down here. And then rewriting, this is x to the negative 1, x to the negative 3/2, and then this negative 1/2, remember when you divide by a fraction, you flip it, you reciprocate it. and then I can simplify this. So this is the limit as x approaches 0 from the right. So I have a -2, and then when I flip this up top, x to the -1 minus a -3/2. So when you divide like bases, you subtract the exponents. The limit as x approaches 0 from the right of -2x to the -1 plus 3/2 is a positive 1/2. Let me clean that up just a little bit. Okay, so now as we take that limit and we plug 0 directly in, I get 0 back out. The square root of 0 is 0. 0 times -2 is 0. Okay, let's look at this one. So that was an indeterminate form to start with, but it was an indeterminate L'Hopital's, and so I had to rewrite it. Okay, so this one, 1 over sine of x minus 1 over x. If I plug 0 directly in, I get 1 over 0 minus 1 over 0. But remember, that's not an answer here. 1 over 0 is undefined, and it says it's going off toward infinity. That's what this is saying. So this implies that this is equal to infinity minus infinity. Now, if it was infinity plus infinity, I'd be done, because infinity plus infinity would be infinity, and that means the limit does not exist. But infinity minus infinity is an indeterminate form. So you better make sure that when you're checking these infinities, whether it's positive or negative. So let's figure out how this happens. So 1 over x, we've looked at this graph many times now. We're approaching 0. So x approaches 0. As I approach 0 from the right, it's going toward infinity. As I approach 0 from the left, it's going toward negative infinity. So to make this a little more straightforward, I'm going to pop a positive in there. So it's approaching positive infinity. Okay, so this piece is going to be my positive infinity. Now 1 over sine of x as we approach 0 from the right. Okay, let's think about sine curve. So this is 1 over x. Let's look at the sine curve. We're approaching it from the right. This is the sine curve. So as we approach 0 from the right, it's getting closer and closer to 0, and it's positive. So that's why I can say it's positive here. So infinity minus infinity. But you have to be careful, because if this would have been, let's say, negative infinity right here minus a negative infinity, I'd be done with the problem, because that would be infinity plus infinity, which is another degree of infinity. But that also means that my overall answer is infinity, which means the limit does not exist. So this is an indeterminate form, not L'Hopital's, so I need to rewrite. And when I have fractions like this, the thing that I should consider is finding a common denominator. So that would be x minus sine of x all over x sine x. So let's go ahead and take that limit. 0 minus sine of 0 over 0 sine 0. And so these are 0 over 0, which is an indeterminate L'Hopital's, which means to do more work. Okay, so the derivative of x is 1, the derivative of sine is cosine, and then down here, out of the blue, product rule. So I have the first times the derivative of the second plus the second times the derivative of the first. So product rule from Calc 1. So let's go ahead and take that limit again. That would be 1 minus cosine of 0. Oops, I forgot I threw that plus sign in. 0 from the right. And then I'll have 0 from the right times cosine of 0 plus sine of 0. Okay. So 0 from the right, cosine of 0 is 1. 0 times anything is 0. So I still get a 0 over 0 here, which is an indeterminate. Ooh, I'm getting worried. L'Hopital's, do more work. And the reason I'm getting worried is I think we're going to have another product rule. So now I have a product rule here for my derivative and then just a regular one. So I'm doing another iteration including another product rule. That's pretty exciting. So the limit as x approaches 0 from the right, the derivative of 1 up here is 0. The derivative of cosine of x is negative sine of x. So the negative is right here, and the derivative of cosine is right here. Okay, so now I'm going to use the product rule. So this piece right here is the piece that needs the product rule. So I have x, the first, times the derivative of the second. The derivative of cosine is negative sine, plus the second times the derivative of x, which is 1. So that is the product rule right here. And then I have the derivative of, I have plus the derivative of sine x, which is cosine of x. Okay, so now let's go ahead and plug in. Actually, let's simplify first. Let's do limit as x approaches 0 from the right. So my numerator I have sine of x. In the denominator I have cosine x. I have 2 cosine x minus x sine x. So let's go ahead and take that limit now. So I'd have the sine of 0. And then in the denominator I'm going to have 2 cosine of 0 minus 0 sine 0. So sine of 0 is 0. Cosine of 0 is 1. Sine of 0 is 0. So this is 0 over 2, which is 0. We're always getting zeros and ones, it seems like. Okay. So you can see that most of this, there's a little bit of calculus in here when we do the derivatives, but really it's a lot of simplification. Let's look at the limit as x approaches 0 from the right of 1 plus x, and then our exponent is 1 over x. So we go ahead and take the limit, and this would be 1 plus 0 to the 1 over 0. Okay, but let's look at the graph of 1 over x. We've looked at this one a lot today. As we approach from the right, you can see this is going off toward infinity. So I can actually replace this with infinity. So this is equal to 1 to infinity, which is an indeterminate form, but it's not indeterminate L'Hopital's. So I need to rewrite this. But let's look at this. This is the base right here is a variable because it has 1 plus x, and the exponent is 1 over x, which is also a variable. So when I have a variable to a variable, the hint is always to use a natural log, because the properties of logs allow me to take this variable that's in this exponent and pop it out. So this is a new technique. It's very exciting. So what we do is we set our limit equal to y, and then because I want to get that out of the exponent, I take the natural log of both sides. Okay, now this is a neat little trick. What I'm going to do is swap the log and the limit. So the rule here is the log, the natural log of the limit, can be rewritten as the limit of the natural log. So the limit of the log is the log of the limit, and vice versa. So natural log of y equals the limit as x approaches 0 from the right of the natural log of 1 plus x to the 1 over x. So the natural log, what happened here, the natural log of the limit is the same as the limit of the natural log. Now the whole reason we did that is we want to be able to take this 1 over x and pop it out front, because in the exponent it's causing trouble. So we have the limit as x approaches 0 from the right, the 1 over x comes out front, natural log of 1 plus x. And I bet you see where this is heading. I'm going to have to rewrite this, but first of all, let's verify that we will need to rewrite it. Let's take that limit on the right hand side. This would be 1 over 0 times the natural log of 1. Well, remember, 1 over 0 we don't leave like that. The graph of 1 over x, as I approach from the right, is going off toward infinity. So this is actually infinity. So infinity times 0 is indeterminate, but it's not indeterminate L'Hopital's. So what I need to do is rewrite. Now this is no longer a variable to a variable, but I'm still in the middle of that rewrite from the previous time, so I need to keep that in mind. Now before, what we would do is we would take this and flip it down or push it down into the denominator. Okay, now it's a single fraction. Over here it was a product. Now I've rewritten it as a quotient. So let's see what the log does this time. So I'd have the natural log of 1 over 0. The natural log of 1 is 0. 0 over 0 is indeterminate L'Hopital's now, and so I need to do a little bit more work and figure out what's going on here. So I have the natural log of y equals the limit as x approaches 0 from the right. The derivative of the natural log of 1 plus x is 1 over 1 plus x, and the derivative of x is 1. So let's go ahead and simplify and rewrite that. So I have the natural log of y equals the limit as x approaches 0 from the right, and when I rewrite that, it's just 1 plus x in the denominator. Well, if we plug 0 in here, I get 1 over 1 plus 0, which is going to be the natural log of y equals 1. And I'm not done. My answer is not 1 on this one, because I need to know what y is, not natural log y. So the natural log of what is 1? Let's see if we can rewrite that to figure that out. Well, natural log is log base e of y. And then I can rewrite this in exponential form. So my base is e, my exponent is 1, and the answer is y. So e to the first equals y. So y equal e. That's my answer. That's the definition of e. Isn't that interesting? So the limit as x approaches 0 from the right of 1 plus x to the 1 over x is the definition of the natural number e. It's pretty cool. Let's look at another one. Let's look at the limit as x approaches negative 6 of x plus 6 over x squared minus 36. Well, if we plug a negative 6 in here, I get 0 over 0, which is indeterminate. Now, it used to be, before I knew about L'Hopital's, this was just indeterminate, and the only thing I could do is try and rewrite, factor, simplify, and I certainly can do that here. For a quick note, this would factor into x plus 6 over x plus 6, x minus 6. These would cancel, and I'd be left with 1 over x minus 6. Plug in the negative 6, and I get negative 1/12. Okay, so I could still use those old methods, but I want to try L'Hopital's here, which says to do more work. So that's the limit as x approaches negative 6. Okay, the derivative of x plus 6 is 1. The derivative of x squared minus 36 is 2x. And if I take that limit and I plug in the negative 6, I get negative 1/12. Matches what our old method too. Okay, so we are going to go out with a bang on this one. Last problem. So let's look at the limit as x approaches 0 of x to the 1 over x. So if you want to, hit pause and try and work through this on your own and then see if our answers match up. Okay, so let's go ahead and get started to see if our answers match up here. First of all, I notice that this is a variable to a variable, so I'm kind of thinking ahead. We might be using a natural log here. But let's go ahead and start just by taking the limit. So if I take the limit as x approaches infinity of infinity to the 1 over infinity, remember 1 over x, we've looked at this graph a lot. As x approaches infinity, this is approaching 0. So this is infinity to the 0, which is indeterminate. but it's not indeterminate L'Hopital's. So I need to rewrite. We need to do something with this. But this is where it comes in handy to have remembered that this is a variable to a variable. So that's a hint to use natural log. Okay, so let's go ahead and give that a shot. So first step, we'd set our limit equal to y. Then I would take the natural log of both sides. Now remember, the whole idea of this natural log is so I can pop that 1 over x out front. And I also can recall that the log of the limits is the limit of the logs, so I can swap those. Okay, and now I can pull that 1 over x out front. So I have the natural log of y equals the limit as x approaches infinity of 1 over x natural log of x. Okay, and we've seen this a lot. I'm thinking we're going to have to rewrite, but let's just go ahead and work on it so far and take that limit. So this would be 1 over infinity, natural log of infinity. Okay, what does that look like? Well, here's our 1 over x again, and as x goes toward infinity, this is going towards 0. So this is 0 times infinity, which is indeterminate, but it's not indeterminate L'Hopital's. So I'm going to have to rewrite, just like we were thinking. Okay, so the way I could rewrite this is to take this and take it from a product to a quotient of just natural log of x over x. So let's do that and then take that limit again. We always drag along the natural log of y because when I get done I have to convert back. So when I take this limit now, I get infinity over infinity, which is indeterminate L'Hopital's, and then this next step I'll use for my derivative. The derivative of the natural log of x is 1 over x. The derivative of x is 1. So I could rewrite that. The natural log of y equals the limit as x approaches infinity of 1 over x. Now that limit is going towards 0. The numerator is fixed at 1. The denominator is increasing without bound. So that fraction 1 over x is going towards 0 as x goes to infinity. So what I have here then is the natural log of y equals 0. And now I want just y, so that's log base e of y equals 0. So e to the 0 is equal to y. So y equals e to the 0, which is 1. So my limit here, big shock, right? Y equal 1. Y equal 1. Okay, so we had a lot of steps for these, but we've done a lot of these limits. We're starting to see patterns. One of the patterns that I've been noticing here is we're doing a lot with 1 over x, so knowing your graph for 1 over x I think would be important. So let's look at that. It's in first and third quadrants. This is the limit as x approaches positive infinity, goes towards 0. As we approach 0, it goes toward positive infinity. So that's a good one to know. And I also see that when I have something that's kind of stuck in this form right here with this 1 over x out front, let's scroll up a little bit more, I can take it from a product and rewrite it as a quotient. That seemed to show up a lot as well. So as usual, if you have any questions, please let me know. I'm always happy to help. These are fun to work on for me, so I would be happy to work on them and help you out too. You can send me a message and remind with a screenshot of your work. You can stop by during my office hours, either on campus or online. And then, of course, the slide rule is open as well on campus on the floor above Einstein's in the Devereaux Library. They call it the third floor, but it feels like the second floor to me, so I just say the floor above Einstein's. So, good luck on this assignment. I hope you enjoy it. It's lots of derivatives, lots of algebra. It's a good challenge. Good luck.